So this is our introduction. We're heading towards quantum theory in several lessons ahead. We want to start understanding the structure of the atom, and we're going to have to look at waves to understand the structure of the atom. Okay. Now, Max Planck, a few hundred years ago, realized a relationship between the frequency that was coming from light and how much energy it had. Okay. So he discovered that atoms and molecules release energy in distinctive quantities, distinctive chunks, and he measured them. Now, this distinctive chunks is going to be one of the pieces that will lead to quantum theory. So you can't get any particular energy coming out, you get distinctive energies. Okay. He called those quanta. If you look at a light bulb, we see that energy being released. Okay. Light is an electromagnetic wave. Okay. There is most likely the light bulbs you're looking at, if they're fluorescent, that's mercury atoms being excited, okay. Electrons going to a higher energy level falling down. And when the electrons fall from maybe the 10th ring or orbit down to the second, that will release energy. Okay. So the light we can see from a light bulb is the best practical example to think of right now. So he was able to determine the energy of one of these individual quanta. Okay. It's a constant, which is named after him, Planck's constant times the frequency. Okay. So frequencies refer to the Greek character nu. Now my font doesn't have nu in it, so it looks like a V, but it should be a nu. So H is 6.6-ish times 10 to the minus 34. Joule seconds are its unit. And nu is the frequency, and that's measured in hertz. How many waves go by per second for an electromagnetic wave? So it's not a sound wave or an ocean wave we're used to. It's the type of waves that are in light. Diving into a little bit of wave theory. I've drawn two full waves out, and I want to label some of the important characteristics: frequency, wavelength. I'll mention amplitude, but that's not a variable that factors into the quantum mechanical wave theory that we're going to do. Okay. So the first thing I want to label is wavelength. If you take any two corresponding points, so I'm just going to use A, but B and B prime, C and C prime, D and D prime, where if there's A, that's the top of our wave. When we get to the very next top of the wave, that distance is our wavelength. And we use lambda to represent wavelength. Now, these are going to be very short waves. We might be using micrometers, nanometers, picometers. Okay, 10 to the minus 6 for micro, 10 to the minus 9 for nano, 10 to the minus 12 for pico. Okay. The other important thing we're going to do is look at frequency. We're going to use a nu character for frequency. And this is a count. So imagine you're at that blue dotted line and you're counting how many waves go by that dashed blue line, and it's going to be a count per second. These waves are very short, but they're very high frequency in the at least visible part of the electromagnetic spectrum. Now, 1/seconds is referred to as hertz. So if you see hertz and you're doing unit analysis, you want to write 1/seconds, and then your units should cancel. So I'm filling in the symbols we're going to use. Wavelength is lambda, where frequency is nu. So that's some of our wave properties, talking specifically about electromagnetic waves. Okay. Electromagnetic waves have these perpendicular electric and magnetic components. Now, we're not going to look at the two components separate because they're going to have the same frequency, the same wavelength, and the same amplitude. So perpendicular is just 90 degrees off. So imagine one part of the wave is going up and down. The other part of the wave is just going right to left. But everything is the same about these two perpendicular waves. We will be looking at frequency, we'll be looking at wavelength, but amplitude is just not going to be, again, one of those variables we're going to be looking at. Now, for electromagnetic waves, they all go the same speed. All colors of light go the same speed. Light coming from the sun goes the same speed. TV waves, your cell phone signals going from your phone to your tower, they all go the same speed. It's such a fundamental speed in physics and chemistry, it's given a special symbol, c. So how fast all electromagnetic waves go, c, which c is a speed. You may not think the letter c means speed, but that's what it represents. And you can calculate speed by taking the product of the wavelength times the frequency. And the wavelength times the frequency for everything electromagnetic will be the speed of light. Okay. This doesn't work for waves on an ocean, doesn't work for sound waves, but works for electromagnetic waves. And light is moving. To 3 sig figs, it's 3.00 times 10 to the 8 meters per second. I'm going to switch that out of scientific notation form so you can hopefully appreciate just how fast that is. So I'll get rid of the power of 8. So I'm going to need 8 zeros after my 3. So that's 300 million meters per second. I'm going to switch the units a little bit more. We're kind of used to kilometers, okay, counting by 1,000. So I'm going to divide this by 1,000 to go from meters to kilometers, kilometers. So light is going 300,000 kilometers, not in an hour, in 1 second. It's fast. Way faster than sound, way faster than any physical wave. Okay. Light from the sun, electromagnetic radiation from the sun only takes about 8 minutes to get to our planet. Now it's really fast, but it becomes an issue when distances get really big. When we send a probe to Mars, or if we send a SpaceX rocket to Mars someday, or we send a probe out to Uranus or Saturn, the distances are so big, there is a time delay. We can't send a signal faster than the speed of light. Okay? So you have to deal with those delays. You can't send a rover out to Neptune and have a joystick and tell the rover, move right, move left. The signal can't get there fast enough. Okay? Even though the signal, the electromagnetic wave, would be going 300,000 kilometers per second. Okay? So in 2 slides, you're going to be using some of these relationships to either calculate the energy, the wavelength, or the frequency. We have 3 variables that we can solve for. Let's talk about this electromagnetic spectrum for a little bit. So we have our arrow for increasing energy, which corresponds to increasing wavelength. So this side is our high energy, okay? Because all we care about is frequency. Okay? Energy is a constant times nu. Okay? Okay? So that's our focus. Okay? Now we end up seeing this opposite relationship, okay? As nu goes up, the wavelength is going to go down, or vice versa. So the high energy, high frequency has very small waves. We have the smallest wave on our spectrum. So very tight. Okay. As we get to low energy, okay, we have very low frequency and very long waves. Okay. So, sorry, very long waves, low frequency. Okay. So the highest energy waves that we kind of are used to talking about, gamma rays, very high energy, okay. Small wavelength, lots of cycles per second. They're going to be fatal. X-rays are pretty fatal. The dentist is going to hide behind a lead suit. I had to go to the dentist, my regular X-rays, and it has to be concerning when they're putting a lead vest over me, then they're going to the room away from me and then taking an X-ray. Okay, hopefully that concerns you. It concerns me. X-rays aren't good, but I'm not telling you not to go to the dentist. You wouldn't want that every single day. There's a limit on how many X-rays you should get. So like 1 or 2 a year is okay. 1 a day is not good. Okay. Ultraviolet radiation is also higher energy than visible. Okay. Ultraviolet or UVA, there's UVA, B, C. I don't know if anybody's ever read sunscreen or used it. Maybe your parents just tell you, you don't read the bottle. Sunscreen blocks against UVA and UVB. Okay. UVA comes closest to visible. UVB is higher energy, then UVC is even higher than that. Sunscreen does not prevent UVC from affecting us. We need an ozone layer to block out the UVC. Okay. Sunscreen can help UVA and B from getting through to our cells. Then we get to visible light. And I find this really fascinating. I'm a chemist, not somebody who gets the biological world, but our eyes are sensors that can only pick out this tiny little sliver of frequencies. If electromagnetic radiation happens to be between about 400 and 800 nanometers, our human eye can perceive it, and our brain, for some reason, connects it to a color. Okay. And then you get the whole debate of, is my yellow your yellow? But that's a separate debate. We can only see these slight little nuances of wavelengths. Okay. Then lower energy than even visible light, infrared, radio waves, TV waves, microwaves. Okay? They all have much longer, big wavelengths, low energy, low frequency. Okay? So we need to think of colors very differently. Any color that we see, particularly if it's being emitted from an atom or a molecule, connects to a certain energy. We can calculate that. So, you know, yellow light has an exact energy. It is of higher energy than red. When a body warms up, it starts to emit energy. If you get your stove really hot, you might see it emit red coming off the burner. That's the lowest energy that the human eye can see. As an object gets hotter and hotter, we'll see more and more of the colors. Okay? So seeing blue is a sign that something is much hotter than seeing something red. And then what color do you think you see? If something is so hot that we see all the colors, the human eye will perceive white. So white does not have a frequency. White is all frequencies. A continuous spectrum is white. Okay. So our brain, again, I find this fascinating and weird. If our brain gets all of these frequencies, it doesn't see a rainbow. It perceives a white color. Now, light bulbs or light bulb manufacturers can play with what frequencies the light bulb produces to tweak the color, or potentially have a diode inside the bulb that you can in real time change the color by changing the wavelengths that are being emitted. So we got this electromagnetic spectrum. We can calculate the energy. We can calculate the wavelength given the energy, and we're going to end with a little bit of that math. So let's do some calculations. Planck says that energy or light is going to come off in these distinctive quanta. Well, how much energy is there in one quanta? So we're going to look at if you have one of the smallest unseparatable chunks of red light, how much energy is that? Okay, how much is each quanta of red light? And then we're going to compare that to one quanta in a microwave. And then we'll look at what if we had a mole of something. So I'll get started with the red light. I guess I was going to do that in blue, but I'll do the red light in red in this slide. So red light, we want the energy of an individual quanta. So energy is Planck's constant times frequency. So energy is 6.63 times 10 to the minus 34 joule seconds are the units to his constant, and then we have to multiply that by the frequency, which we don't have. We know that red light is about 700 nanometers, so that's coming from our diagram. So red light, okay, I'm just using roughly 700. I'm not using sig figs with this. Okay, I'm just ballparking it. Okay, so smack dab in the middle of the red, about 7. Okay. Now we can use the speed of light is the wavelength times the frequency. So C is lambda times nu, and we need that nu because that's what goes into Planck's equation. So I'm going to rearrange for nu. Nu is equal to the speed of light c divided by the wavelength, and we're just going to have to watch our units. The relationships are fairly straightforward. There's no powers, there's no logs, but you have to watch your unit analysis. Okay, that will tell us that black underline. So the speed of light, 3.00 times 10 to the 8 meters per second. Okay. And we're going to need the wavelength in meters. Okay. We can't mix our units. So we have to think of what does nano mean. Nano represents 10 to the minus 9. So micro is 10 to the minus 6. Nano is 10 to the minus 9. Pico 10 to the minus 12. So when you're just trying to swap out that nano, you can straight get rid of the n and replace it with what it means. It means 10 to the minus 9. So I just took that n and straight substituted its meaning. Okay. And I get a little under 4.3 times 10 to the minus 14, 1 over seconds, and 1 over seconds can be switched to hertz. You kind of need to be comfortable. You could go 1 over s or hertz, it doesn't matter. Hertz is 1 over seconds, and there's seconds on the top. So seconds and 1 over seconds will cancel. Okay? This is where you may want to not use hertz, but use 1 over s. all that's left for units is joules. So the energy of one unbreakdownable quanta of red light is 2.84 times 10 to the minus 19 joules. Not very much. One little quanta of red light, or a human eye wouldn't even pick up. But there are hundreds of millions of trillions of quanta of red light coming out of a red light bulb every second. So let's compare that to a microwave. Now, a microwave has a wavelength of a centimeter. So we went from a very tiny wavelength way up to a centimeter, 10 to the minus 7 or so, up to 1, or 10 to the minus 2 meters, centa being 10 to the minus 2. I want to do this a little differently. Some of you hopefully maybe said, could you just combine the two formulas? Okay. You can do a substitution. You can do it in 2 steps like I did, or just substitute this relationship in for nu. Okay. So I want to show you that way, and both ways are fine. So energy is h nu. You've got to realize that. But what is nu? It's hidden. It's just c over lambda. So instead of nu, I'm going to go c over lambda. It's the same thing, just in 1 step. It's probably more efficient to solve it this way. So Planck's constant, you'll get on a AP formula sheet. You don't have to memorize it. We just have to watch our unit C. We need it in meters per second. And then we need wavelength, and I'm going to stick units in right away. We need it in meters because we have meters per second. So we have to convert that 1 centimeter to meters, centimeters, centi, counting by thousands. So 1 centimeter, sorry, counting by hundreds. So 1 centimeter, if we divide that by 100, we'll convert it to meters. And then I had 1.00. So I'm not showing my centimeter to meter conversion. So my meters canceled, my seconds with inverse seconds canceled. Again, I'm left with just joules, same as when I did this in 2 steps. And I get 1.99 times 10 to the minus 23. So let's compare. How does 1 quanta of red light compare to 1 quanta from a microwave, the smallest pieces that we can't break down? Which one's bigger? So we got negative 23 and negative 19. Okay? The smaller or the less negative the power, the bigger it is. So minus 19 is much bigger than minus 23. There's actually 4 powers different. Okay? And each power is a 10. So there's like 10,000 times more energy in 1 red quanta than 1 microwave. Microwaves heat our food by A, there's a lot of quanta, and B, they're focusing right in, okay, to heat our food. The same way we go out in the sunlight, we don't die, we're fine, but you have a magnifying lens and you focus that sun all to 1 point and you would burn yourself or start a fire. Okay, same type of principle with a microwave. Last little bit, this is counting by 1 quanta. Okay. We may want to do this for 1 mole. In Science 10, we briefly counted moles of things. Okay, you can have a mole of hydrogen atoms, okay? A mole of oxygen atoms. Okay? A mole is just 6.02 times 10 to the 23 of anything. Okay? So instead of having one quanta from a microwave, which is that number, if we had a mole of quanta from a microwave coming off, we just have to multiply that green number by a mole. So 1.99 times 10 to the minus 23 joules, and that's joules for 1 unit. So that's how many we have of anything in a mole. Here we're counting, this is really joules per quanta, and that's how many quanta are in a mole. So if you had a mole from a microwave, it works out to about 2 joules. So still not a ton of energy. So I believe I read that wrong. 12. I missed the preceding. So most of the time on a quiz or test, I'll ask you about the energy in 1 quanta. If I ask you about a mole, you just multiply by Avogadro's number. So watch your units and your conversion, and you should be fairly successful.